Okay, good morning. Next Monday, between 4 and 5 in the afternoon, I have a meeting. So Professors Ruan and An will take care of that hour. If you have any questions, you could consult them. Their offices are listed in the first handout I gave you. The Monday after that, November the 1st, there will be a midterm, 一个期中考试。It's just for 1.5 hours. 就是 instead of the lecture, you'll have the 期中考试。Last time we first talked about the geometrical proof that if a body has an initial position and a final position, a rigid body with a initial position and a final position, we want to prove that there is a point. If a rigid body has one point which is fixed, and it has an initial position and a final position, then there is a point, there's an axis on the body which is not moved in that motion. Remember that has nothing to do with the intermediate steps. You can have a body, this point is fixed, you can move it in whatever way. We don't care about the intermediate steps. We only care about the initial position and the final position. 只是最早的跟最后的，中间不管。那么要证明的是说，从开始到尾巴，这个中间有一条线是不动的，是一个 rotation。有同学pointed out that in my proof there is a defect because I had proven that A prime, B prime, N 跟这个 A prime, B prime, M prime 是两个一样的三角形，的三边 the three sides of A, B, N and the three sides of A, B, M prime are respectively identical. So I said that M must be equal to M prime. And some students pointed out that that's not entirely correct because how about this one? Could A prime, B prime, M prime be like this? It's a good, that's a correct point. There's a defect in my previous proof, but it can be easily gotten around because in A, B, N, if you go around from A prime to B prime to N, the triangle is on your left side. And so would this be. But with this one, A prime, B prime, when you go around A prime, B prime, M prime, the triangle is on your right side. Of course, if you have a rigid motion, a triangle cannot change from a right-handed circle to a left-handed circle. So therefore, this one is not. So we still have M equal to M prime. Actually, this argument is dependent on the fact that on a sphere, if you have a triangle of the first kind, namely when you go around it, this triangle is on your left side. If you now move this triangle on the surface, it remains that way. Therefore, the surface of the sphere is called orientable. Not all surfaces are orientable. A Möbius strip this is the simplest and the most famous example. It's if you take a strip of paper, if you take a long strip of paper, if you take a long strip of paper and glue it together this way, there's nothing strange about this. If you draw a triangle on it, going counterclockwise, you move the triangle on the surface, when you come back it will be the same. But if you twist this 180 degrees and then glue it together, then you have a surface like this. Then it becomes a non-orientable surface, because if I have a triangle here with the going left-sided, when I go around, it goes to the other way. So there are differences between orientable and non-orientable surfaces. And that is a very important difference when you talk about topology. Topology is a 20th century main aspect of mathematics. Maybe I told you this before. In the 19th century, mathematics had three important divisions: analysis, algebra, and geometry. In the 20th century, there is the new idea that's greatly developed, and that's called topology. So the main areas of mathematics consist now of four. And what is found is that the four are deeply related. Okay, last time we had the following formula. X prime is equal to I prime, J prime, K prime. And we have the formula X prime is equal to X gamma. And the formula gamma R prime is equal to R. And the formula gamma is equal to 1. And determinant of gamma is equal to 1. This gamma matrix is, so we say gamma is an element of SO3. Now I want to give another proof. Of gamma tilde equal to 1. Let us write this equation X prime equal to X gamma explicitly. It's I prime, J prime, K prime times some 3 by equal to I, J, K times a 3 by 3 matrix. Let's write the 3 by 3 matrix as A, B, C, A prime, B prime, C prime, A double prime, B double prime, C double prime. So I take the first element of both sides. That's the unit vector in the x direction of the new system is equal to AI plus BJ plus CK by matrix multiplication. What does that mean? That means A, B, C are the A in the x direction, B in the y direction, C in the z direction. The three of them add together is I prime. So that means A, B, C are the components this formula means ABC are the respective components of I prime along the XYZ direction, along the IJK direction. Similarly, A prime, B prime, C prime. Let us give that a name. Let's call it, we regard it as a vector. We call it rho 1. So rho 1 is this vector. It is the unit vector of the prime system. Similarly, we have rho 2 equal to this, rho 3 equal to this. In other words, we take the matrix gamma and consider the first three elements as a vector, the next three elements as another vector, the last column, three elements, as a third vector. So I now have three vectors, rho 1, rho 2, rho 3. Then it's clear that rho 1 squared, so therefore rho 1 squared, rho 1 tilde rho 1 is the absolute value squared of rho 1. And that has to be equal to 1 because that's the length squared of I prime. So this has to be equal to 1. And similarly, this has to be equal to rho 2 wiggle, rho 2 is equal to rho 3 wiggle, rho 3. Because rho 1, rho 2, rho 3 are nothing but the three new unit vectors, I prime, J prime, Z prime, K prime. Now if I take rho 1, rho 2, that's the dot product between rho 1 and rho 2. If you have two vectors, this is the scalar product. The scalar product between rho 1 and rho 2 is the scalar product between I prime and J prime. And by definition, it's a new coordinate system. The three axes are all perpendicular to each other. So therefore, this is equal to 0. So these two lines really mean that the rho 1, rho 2, rho 3 are unit vectors. This line means rho 1, rho 2, rho 3 are orthogonal to each other. Orthogonal means treated. So this matrix now, we now have the geometrical meaning of this matrix. The first column and the second column and the third column are three unit vectors which are perpendicular to each other. That statement is equivalent to the statement. That statement is equivalent to the statement gamma with tilde is equal to 1. Why? Because I write down this rho 1, this gamma. Let's consider what this is. This is this matrix A, B, C, A prime, B prime, C prime, A double prime, B double prime, C double prime. Gamma tilde is the same thing, only turn around. So it's A prime, A double prime, B, B prime, B double prime, C prime, C double prime. This is the definition. Now you see the first corner element is ABC times ABC. That's rho 1 squared. That's equal to 1. If I take this next element is this times this, and that's rho 1 times rho 2, which is 0. The third one is ABC times A double prime, B double prime, C double prime. That's rho 1 times rho 3, and that's equal to 0. So you see that this equal to I. Gamma tilde gamma equal to I merely means that these three vectors, if you consider the three columns of gamma as three vectors, then the three vectors are orthonormal. Ortho means that they are orthogonal. Normal means that they each of length 1. But from this we know that gamma tilde is equal to gamma inverse. And from that we know that gamma tilde is equal to 1. These are algebraically true. So what is the meaning of gamma tilde? We just had the gamma tilde gamma equal to 1. This one is gamma tilde is also equal to 1. Now what's the geometrical meaning of gamma tilde equal to 1? It is that if you take this, if you consider this to be a vector, now instead of taking columns, you take rows. This to be one, let's say called eta 1, eta 2, eta 3. Then eta 1, eta 2, eta 3 form an orthonormal system. So the gamma matrix has a property that either you take the columns, then you get three vectors which are orthonormal to each other, or you take rows, they also form an orthonormal system. Okay, what I just said, everybody has to understand, because whether you are an experimental physicist, whether you will become an experimental physicist or theoretical physicist, 3x3 matrices, properties of 3x3 matrices you have to be familiar with. And one of the most important type of 3x3 matrices is gamma. So with all this preparation work, we are now ready to give an algebraic proof of what we proved last time, geometrically. Namely, from one position, if one point is fixed, into another position, in that motion, there has to be one axis which is not moved. So, in order to do that, we must first introduce a new algebraic idea. It's called eigenvalue. Now everybody has to understand eigenvalue. If you cannot understand eigenvalue, you cannot understand quantum mechanics. Quantum mechanics is based on the concept of eigenvalues. So the definition of eigenvalue is very, very simple. We have a matrix gamma. I take gamma, in other words, I take A minus lambda, B, C, A prime, B prime minus lambda, C prime, A double prime, B double prime, C double prime minus lambda. I take the gamma matrix and subtract lambda from each of the diagonal elements. If I expand the determinant, the first term is A minus lambda times B prime minus lambda times C double prime minus lambda. If you multiply that out, you get the lambda cube minus lambda cube term plus alpha lambda squared plus beta lambda. So you have the cube term, square term, linear term, and you have the term without lambda. The term without lambda is the determinant of the term which does not involve lambda. Means you erase all the lambda, so it's the determinant. That determinant we know is equal to 1. So so we know it's plus 1. Does everybody understand what I just said?
Yeah.
Okay, I now have an algebraic equation with the real coefficients. Everything is real so far. So I have cubic equation. Now, a cubic equation must have one real root. How do we prove this? Does anybody know why a cubic equation must have one real root? Okay, raise your hand if you know how to prove this. I'm disappointed. Nobody knows how to prove. I thought Tsinghua has the best students. Is it because you are too shy? Okay. 你讲一下子为什么一个 cubic equation with real coefficients must have a real root?
因为这个一个三次这个函数它的这个值域是 r， 也就是说它可以设满整个实数。
对 Because if you consider that polynomial, let's write this as a polynomial. When lambda 等于 infinity 的时候 when lambda goes to positive infinity, when lambda is very, very large, you can neglect all those terms. So it becomes minus lambda cube. So p is negative. When lambda becomes minus infinity, again you can neglect these terms. This term becomes positive. So from lambda equal to minus infinity to lambda equal to plus infinity, that curve has to go from the bottom to the top. So in the process it has to cross. When lambda is go to positive infinity, it has to go to negative. It goes this way. When lambda is minus infinity, it has to go this way. So therefore the curve has to be something like this. In which case it has 3 roots, but it can also be this way. In which case it has 1 root. In any case it has to cross the x-axis at least once. So there must be 1 real root. How about the other 2 roots? So there's 1 real. The other 2 the other 2 roots must be complex conjugates of each other. But it either has 3 roots. Let me now state a theorem. One root, the 3 roots. These roots are called eigenvalues. Eigenvalue is a German word originally. Eigen is a German word. But because this idea originated mathematically from Hilbert in the beginning of the 20th century, and physics-wise, from Heisenberg and Born and so on and so forth, all who were German. So they invented the term eigen, and now it's transported into English. So we call it eigenvalues. Sometimes it's called characteristic values, but almost nobody uses that anymore. The three roots of gamma are of the form 1 exponential I theta and exponential minus I theta. Proof. First, one root must be real. If another root, it could be that another root is also real, but let's first discuss if another root is complex. Then the third root must be the complex conjugate, because the roots complex roots form in pairs. So therefore it is of the form eta. Eta is a real number, xi and xi star. I now want to prove that the xi has to have an absolute value equal to 1. So here epsilon. I now want to prove that epsilon has to have absolute value equal to 1. Because lemma epsilon equal to plus minus 1. Because epsilon is an eigenvalue, that means gamma minus epsilon I determinant is equal to 0. That's the definition of epsilon. This is a 3 by 3 matrix. If a 3 by 3 matrix has determinant equal to 0, that implies that there's a column vector psi such that this is equal to 0. Gamma minus epsilon I is like this. Psi is a column. You are still in linear algebra. Have you gotten to this? If the determinant of a 3 by 3, if a 3 by 3 determinant is equal to 0, there always exists a non-vanishing psi such that this becomes 0. That's this formula. If you have not learned that yet, you will learn it very soon. That's one of the fundamental points of linear algebra. If that is the case, that means gamma psi is equal to epsilon psi. That's the fundamental property of an eigenvalue. Whenever you have an eigenvalue, psi, epsilon, any of the eigenvalues, there always exists a non-vanishing psi, such that, which is a vector, such that gamma operating on psi gives you another psi. So gamma psi is the same as its original one, except that there is multiplied by epsilon. And now we can easily prove that the epsilon's absolute value has to be plus minus 1. Because if I now operate with gamma repeatedly on this, I now take a gamma square psi. Then it's epsilon gamma psi is equal to epsilon square psi. If I multiply by 3 times, is equal to epsilon square gamma psi is equal to epsilon cube psi. What this means is that by repeatedly operating on, you can now make this as large as possible. But gamma square is also an orthogonal matrix. If gamma is an orthogonal matrix, gamma is a rotation. Gamma square means you do the rotation twice. Gamma 3 times means you rotation 3 times. So all these are rotations. In other words, they are all orthogonal matrices. Gamma n is also an orthogonal matrix. It's also orthogonal. What this says, if epsilon absolute value is not equal to 1, is that you can now find an orthogonal matrix whose eigenvalue is as large as you want. You just keep on multiplying by epsilon, and that's not possible. So therefore, that means what we conclude eventually is that the epsilon absolute value square has to be equal to 1. In other words, epsilon is equal to plus minus 1. This is the idea, but you may not be too happy because logically, how do I prove I may have a gap here. Anyway, I'll come back to this next point. The idea is that if you have an orthogonal matrix it cannot have very large eigenvalues. It's just because of the reason I said. You cannot keep on multiplying it by itself and get larger and larger eigenvalues. So that gives us the result that epsilon is equal to plus minus 1. Now if epsilon is equal to minus 1, then the product of the three eigenvalues is minus 1 times xi star, which is equal to a negative quantity. But the three eigenvalues product has to be equal to 1. If you look at the formula, if you look at because this is plus 1, this is minus sign. That means the three eigenvalue multiplied together has to be equal to 1. That means if the three eigenvalues, lambda 1, lambda 2, lambda 3, has to be equal to 1. So, if epsilon is equal to minus 1, the product is equal to minus 1 times xi star, and that's equal to minus 1, not plus 1. So that's not possible. So therefore, but lambda 1, lambda 2, lambda 3 is equal to 1. Therefore, epsilon is equal to plus 1. So through this series of arguments, we finally got the statement that the lambda, there exists one eigenvalue which is equal to plus 1. Now if that is equal to plus 1, then we immediately have psi, there is an eigenvector. Eigenvalue, the epsilon or lambda is called an eigenvalue, and the associated psi is called an eigenvector. Eigenvalue and eigenvectors are the fundamental concepts of quantum mechanics. So the mathematical basis of it is what we are now discussing. If we have an epsilon which is plus 1, then its associated eigenvector psi has the property. But what does that mean? That means that if psi is a vector R, that means the gamma operating on psi is not changed. So that means that psi is the axis of rotation. This is precisely what we concluded from the geometrical proof. So after all this machinery of algebra, we got into this. But there are still a few points that we need to tighten up, because we have the assumption proof 1. One root must be real. If another root is complex, then blah 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 blah. But how about if another root is not, no other root is complex? So 3. If all 3 roots are real, then I'm not going to go into this detail. Then there are only 2 possibilities. It either is 1, 1, 1, or it's 1, minus 1, minus 1. If all 3 roots are real, then it has to be this way. Both of these are limits of what we just said. What we had earlier are 3 roots, 1 exponent. Just a minute. Furthermore, xi star 1, xi star is equal to 1. So xi absolute value is equal to 1. So therefore, the 3 roots are 1 exponential I theta, exponential minus I theta. So So in that case, when theta goes to 0, you get the 1, 1, 1. When theta goes to pi, you get 1 minus 1 minus 1. So therefore, what is left here are really limiting cases of the first one. Okay, let's review now what we have found. We have found that if we look at the three eigenvalues of gamma, we find the eigenvalues, three eigenvalues, which is 1 exponential I theta, exponential minus I theta. Each of them is associated with a eigenvalue. So we have a gamma. With this one I call it psi 3. With this one, let's call it gamma phi is equal to exponential I theta phi. Every time you have an eigenvalue, you have an eigenvector, such that gamma operated on that eigenvector is equal to the eigenvalue times the eigenvector. For this one, you just take the complex conjugate of it. If I take the complex conjugate of it, since gamma is real, this is not changed. Phi star is equal to exponential minus I theta phi star. So the eigenvectors for exponential I theta and the eigenvector for exponential minus I theta are complex conjugates of each other, explicitly written here. Now let us write this out explicitly. But what I'm going to do now is to show you that the theta has a geometrical meaning, in fact. So I now explicitly write this down. I get gamma phi. Let me define write phi as psi 1 plus I psi 2. Phi is complex. Psi 3 is real. How do I know it's real? Because it's the solution of gamma minus I. Determinant is equal to, that's the characteristic equation for the eigenvalue 1. And therefore, and this is a real 3 by 3 matrix. Its determinant is 1, so I have a vector which dot product into it gives you 0, and that's the eigenvector. Because this is a real matrix, so that the eigenvector is also real. So by definition, psi 3 is real. But here, everything is complex, so phi is in general complex. So I split it into psi 1 plus I psi 2, and then of course phi star becomes psi 1 minus I psi 2. So now I write both of these equations. No, let me first write take this. I'll now take the tilde of this. You remember when you take tilde, you get the product of the tildes, but you have to reverse the order. I now multiply this equation onto this equation. So the left side is psi the right side is but this is 1, so therefore I get let us now assume theta not equal to 0. Theta equal to 0, we get to that 111 case. So let us assume in general, assume theta not equal to 0. If theta is not equal to 0, this formula says exponential I theta minus 1 times psi 3 tilde phi is equal to 0. This is not equal to 0. So therefore, psi 3 tilde phi has to be equal to 0. But that means psi 3 tilde times psi 1 plus I psi 2 is equal to 0. Psi 3 is real, psi 1 is real, psi 2 is real. So this equation is a complex equation whose real part and imaginary part have all to be 0. So we have psi 3, psi 1 is equal to 0, is equal to psi 3, psi 2. So we have proven that psi 1 is perpendicular to psi 2, that psi 3 is perpendicular to psi 1, psi 3 is also perpendicular to psi 2. I now want to prove that psi 1 and psi 2 are also perpendicular to each other. And when I do that, I would get the geometrical meaning of theta. So now I write that the two equations, I write the gamma psi 1, gamma phi. I write gamma phi is equal to exponential I theta phi, which means gamma times psi 1 plus I psi 2 is equal to exponential I theta psi 1 plus I psi 2. I take the complex conjugate of this equation, which is the other equation. Gamma is real, so it's psi 1 minus I psi 2 is equal to exponential minus I theta psi 1 minus I psi 2. I add, then I get gamma psi 1 I get 2 gamma psi 1 is equal to exponential I theta plus exponential minus I theta times psi 1. Who knows what is? What is the exponential I theta plus exponential minus I theta? It's 2 cosine theta. If you are not familiar with this, quickly familiarize yourself with that. So I get 2 cosine theta psi 1. Plus I times plus I psi 2 times exponential I theta minus exponential minus I theta, and that's 2I sine theta. So I eliminate all the 2's. I get gamma psi 1 is equal to, now instead of cosine theta I write C. So C psi 1 minus I is minus S sine 2, S psi 2. C is equal to cosine theta, S is equal to sine theta. Similarly, I subtract the 2 equations. After you subtract the 2 equations, you get gamma psi 2 is equal to S psi 1 plus C psi 2. And now let us, I now want to calculate, I have now 2 vectors. One is psi 1, one is psi 2. And when you multiply, when you operate with them on gamma, you get the right hand side. Now let us calculate psi 1, the length of psi 1. The length of psi 1, you just take this and take its tilde and multiply it. And that's equal to psi 1 gamma by definition, since gamma is orthogonal, so you have this. But now I can substitute this equation in. So I get C psi 1 minus S psi 2 times C psi 1 minus S psi 2. So I get C squared psi 1 tilde psi 1 plus S squared psi 2 tilde psi 2 minus 2SC psi 2 tilde psi 1. Psi 2 tilde psi 1 is equal to psi 1 tilde psi 2. So the 2 terms give you the same. If I move that onto similarly, I get psi 2 tilde psi 2. After some computation, you find this is equal to S squared psi 1 tilde psi 1 plus C squared psi 2 tilde psi 2 plus 2SC psi tilde psi 2 tilde psi 1. So I have these 2 formulas. Let's define D as the difference. definition. So I now subtract. I get D. On this side, I get C squared minus S squared, C squared minus S squared times this difference the psi1 absolute value squared, psi1 absolute value squared has the coefficient C squared S squared. This difference has the coefficient minus C squared S squared. So the two combine to D. So these four terms together becomes this minus 4 SC psi 2 tilde psi 1. If I now move that onto the side, I get 1 minus C squared plus S squared D is equal to minus 4 SC psi 2 tilde psi 1. One minus C squared is S squared, so I get 2 S squared D is equal to minus 4 SC and then let's call this equation 1. Now I take these two equations and I take this, I now calculate psi 1 tilde psi 2, and that's equal to psi 1 tilde gamma psi 2. Because gamma is orthogonal. And I now use those two formulas. So I get CS psi 1 tilde psi 1 minus CS psi 2 tilde psi 2 plus C squared psi 1 tilde psi 2 minus S squared psi 1 tilde psi 2. I just multiply those two. It's these two formula. And that is equal to SC times D. That's what this is. Plus C squared minus S squared psi 1 tilde psi 2. I move that onto the left side. I get 1 minus C squared plus S squared psi 1 tilde psi 2 is equal to CSD. But that's 2S squared psi 1 tilde psi 2 is equal to CSD. This equation I call 2. So I now have two equations which relate the ratio between D and if you examine those two equations, you find that the only possibility is that they are both equal to 0. Because You do this yourself. Within a few minutes, you prove that both of them are equal to 0. What's the meaning? The meaning is that d equal to 0 is psi1. So the length of psi1 is equal to the length of psi2. And this says that they are orthogonal. So now review what after all this algebra we are doing. We have proven that there are three vectors, psi1, psi2, psi3, all real. We had previously proven that psi3 is perpendicular to psi1 and also perpendicular to psi2. Now we have proven that psi1 and psi2 are perpendicular to each other. So all three of them are perpendicular. And this statement says that the length of psi1, psi2, psi3 has never been fixed. When we defined psi1, when we defined psi3, psi3 is the eigenvector of gamma. How did we obtain an eigenvector? We take gamma minus lambda I, determinant is equal to 0. Therefore, the 3 by 3 matrix has a linear vector which would dot into the matrix and equal to 0. But you can multiply that vector by 5, by 15. So the length of that vector is not defined. So we can arbitrarily define the psi1 as the length of psi3. Let us define it to be 1. Now, similarly, psi1 and psi2 come from phi, the complex vector. The complex vector also has an arbitrary length. So we change the length so that psi1 absolute value squared is 1. And because we had just proven that psi1 absolute value squared is equal to psi2 absolute value squared. So now all three of them are orthogonal. In other words, we can choose psi1, psi2, psi3 to be orthonormal. Ortho means mutually orthogonal. Normal means absolute value equal to 1. And because psi3 is an eigenvector, that means the gamma operating on it is not changed. How does gamma operate on psi1 and psi2? What happens? It's this formula. When gamma acts on psi3, it is not changed. That's the axis. So now we want to know what happens to gamma operating on, let's call these equations A. When gamma acts on psi1 and psi2, we use A. There are three vectors, psi1, psi2, and psi3. Let's choose to draw a diagram psi1, psi2. Now let's go to equation A. Gamma psi1, let's call that psi1 prime. the new psi 1, is equal to C psi 1 minus S psi 2. Gamma psi 2 is equal to S psi 1 plus C psi 2. That's A. So what is then that will be called psi prime, psi 2 prime. Now what is the C psi 1 plus C is the exponent cosine theta. So if I now draw then from here to here is cosine theta times psi 1. From here to here is sine theta minus sine theta psi 2. So this vector now is psi 1 prime. You decompose psi 1 prime along psi 1 and psi 2, you find that the coefficient for psi 1 is cosine theta, for psi 2 is minus sine theta. So, and similarly this, so this is psi 2 prime. So the geometrical meaning of equation A merely means that psi 1 prime and psi 2 prime are two orthogonal vectors which are rotated from psi 1 psi 2 by angle theta. So now we know when gamma operates on any vector, all it does is just rotates it around the psi 3 axis by the angle theta. Here we see the intrinsic meaning of eigenvalues. The eigenvectors tells you how to rotate. The eigenvalue itself tells you how the rotation, the magnitude of the rotation. So the algebraic concept of eigenvalues are deeply related to the geometrical meaning. I choose to struggle through this algebra, not only because it illustrates this problem, but because we learn something along the way about the properties of an orthogonal matrix, and that is of essential importance, especially when we go to quantum mechanics, because quantum mechanics is based on matrices, and so properties of matrices are extremely important for quantum mechanics. By the way, let's review what is the meaning of psi 3, the eigenvector, and what is its geometrical meaning. Psi 3, what we have proven, that the key idea is that we have an orthogonal 3 by 3 matrix, and it has 3 eigenvalues, and we proved that one eigenvalue is 1, and the associated eigenvector is the axis of rotation. Once you understand this, you would immediately be able to generalize it. How about we do a 4-dimensional rotation? A 4-dimensional matrix, for 4-dimensional rotation is a 4 by 4 real matrix which is orthogonal. That means the 4 columns are all orthonormal to each other. And okay, so we do the same thing. It has 4 eigenvalues. But in that case, it does not have to have a real eigenvalue. because it can be two sets of complex eigenvalues. It could be exponential I minus I theta, exponential I theta and exponential minus I theta. That's one pair. Exponential I theta prime and exponential minus I theta prime. That's another one. Could it have an eigenvalue which is larger than 1? It can't, for the same reason. If it has an absolute value which is bigger than 1, you just keep on multiplying this multiplying this orthogonal matrix onto itself. It remains orthogonal, and yet the eigenvalue would blow up. Eigenvalues of orthogonal matrix cannot blow up. So therefore, it has to be of the form exponential I theta, exponential minus I theta. But in that case, there's no 1. If there's no 1, there's no axis of rotation. So for all even dimensions bigger than 2, it's not necessarily a rotation. For all odd dimensions, there has to be a real eigenvalue. Therefore, it has to have an axis. But if you have 5 dimensions, let's say you have one eigenvalue which is a 1, then the other 4 eigenvalues have to be of the form exponential I theta, exponential minus I theta, exponential I theta prime, exponential minus I theta prime. What that means is that there is one axis which is not moved. Then the remaining 4 dimensions divide into 2 perpendicular 2 dimensions. In one 2 dimension, you make a rotation of angle theta. In the orthogonal dimension, you make a rotation of theta prime. So the algebraic concept has the advantage that you can easily generalize to higher dimensions. And this is, of course, what occupies much of mathematics and occupies much of recent physics, because the question of why we have 4 dimensions and how to unify all the forces get into very complicated mathematics of higher dimensions. Okay, we have been talking about SO3. SO3, that S means that the determinant of gamma is equal to 1. But when we prove, you remember, if you have gamma tilde gamma equal to 1, you take the determinant, then you get the determinant of gamma tilde times the determinant of gamma, which are the same, because when you take a tilde, the determinant doesn't change. So from this it follows that determinant of gamma is equal to 1. No, determinant of gamma squared is equal to 1. So that means the determinant of gamma is equal to plus minus 1. And we have chosen determinant of gamma equal to plus 1. But what happens if you talk about determinant of gamma equal to minus 1? Does anybody have a brilliant idea about how to deal with orthogonal matrices whose determinant is minus 1? Yes?
我们可以用镜面映射，就是一个平面镜。
我耳朵不好，你讲的。
我们可以用镜面映射，就是用一个平面镜把那个东西映到那个镜子底下。
这个 idea 是对的。OK， 我们来研究一下。他说我觉得他的意思是说， 这不是一个伽马吗？你先把这个伽马写成一个，希望还没有摔坏。他把它乘上一个，我猜想他的意思是乘上这么一个 3 by 3的 matrix 是 diagonal 的，1 负1，这个意思就是 x 等于 x prime，y 等于 y prime，z 等于 minus z prime， 那就是个 reflection， 所以这是一个 reflection。你把这个乘起来以后，你叫做 gamma prime， 那你看容易证明 gamma prime 也是orthogonal。可是 gamma prime 的 determinant 就是1了，因为 gamma prime 的 determinant 是等于这两个 determinant 乘起来，所以是 -1 乘 -1， 所以变成 +1， 所以你就可以研究这个东西，然后你把这个东西再翻到那边去就行了。这个 idea 是 correct， but there's a better idea. Anybody knows a better idea? It's just a slight variation. Don't use this one. Use -1, -1.你把它乘上 -1, -1 了以后，这个叫做一个 inversion。inversion 什么意思？就是你三个dimension x 各有一点，你把它 diametrically 对于 origin opposite 那点，你叫它 negative coordinate。如果你把它乘上这个了以后呢，当然这个 gamma double prime 的 determinant 就是1了。可是这个比刚才那个好的地方，所以这个是一个 commute。这个跟就是这个东西一个 matrix 乘上一个 -1是一个最简单的事情，所以这个是一个 better idea. In other words, if you want to discuss a 3 by 3 orthogonal matrix with determinant -1, it's best that you write it as -1, then this -1 multiplied by an SO3. But this trick does not work when you have 4 dimensions. Because in 4 dimensions you write -1, -1, its determinant is +1. So that does not serve your purpose. So what this has illustrated, we have in the last 5 minutes said 2 things, which illustrates odd dimensions and even dimensions have some fundamental differences. Okay. After all these complicated mathematics, which are not in the book, so therefore I'm not going to have any questions in the examinations about this. But if you want to, when you go to more advanced mechanics, you have to go through what we have just gone through. Now, whether you use geometry or you use algebra, you eventually get this formula. In other words, when a rigid body moves, you can characterize it by 2 vectors. One is V, center of mass. The other is omega. The omega is the rotation around the center of mass, where R is relative center of mass. This equation is an equation in kinematics. Kinematics means mechanical quantities not related to dynamics, not using Newton's equations. In other words, you can write down the equation even before Newton, because you don't have F equal to ma. Now we talk about dynamics. Dynamics of rigid body. I write mi ri double dot arbitrary origin, 先 arbitrary origin, arbitrary position for origin. In other words, not necessarily center of mass. This is equal to Fi plus summation. Oh, we had this formula before. This is the external force on particle I. This is the force on particle I by particle J. But if we define, let's define Fii to be equal to 0. Let's define the cell force to be equal to 0. Then you don't have to have the condition. Now we are going to introduce a fundamental concept called angular momentum. We have the linear momentum or momentum, which is mi vi. Angular momentum of ith particle is equal to Ri cross Pi. Pi is the momentum, it's mvi. Ri is from the origin. So here Ri depends on choice of origin. In other words, if I change the origin, then the angular momentum so defined is different. So, if the origin is here, if the particle is Ri is here, and the velocity is this, then Ri cross the angular momentum is on top, going upwards. Now let us calculate Li dot. But we now calculate the sum. So this is the total angular momentum. This is equal to rate of change of total angular momentum. Total means you collect all of the angular momenta of all the particles. Okay, by definition, this is equal to summation mi ri cross ri dot. Now I want to take the derivative of this. This becomes summation mi ri dot cross ri dot plus summation mi ri cross ri double dot. Right? Because I want to take the derivative of this expression, and I have to take the derivative of this one plus the derivative of this one. But this part is 0. Because ri dot cross ri dot by definition is 0. Any vector cross itself is 0. So I only have this part. Now I substitute Newton's equations into it. This becomes summation mi ri cross fi plus summation mi ri cross summation of f Now, the term summation mi ri cross summation j f I has I j and j I terms. 它这 term 有3种，一种是 I 跟 j 一样的，那些都是 zero by definition. Some of them is I and j 不一样的 ，I 跟 j 不一样的 ，it always occurs in pairs. So let's it has these terms and the two together gives Ri cross Fi plus Rj cross, which is equal to Ri minus Rj cross, because this term is equal to minus Newton's third law. Now what is this? This is the force between j and j open and I. This is the vector difference between the two. So if this is I, this is j, this is the origin, this is Ri, and this is Rj, and Ri minus Rj is this. Ri minus Rj is in the direction of I and j, but the Fji is also in that direction. Now two vectors which are parallel has no cross product, so this is equal to 0. And that is the reason why angular momentum is so important. It's because the internal force contribution to the angular momentum's derivative cancels each other. Therefore, we now have the grand theorem that total angular momentum derivative is equal to, this whole term is 0. So it's equal to summation no, there are no mi. Just a second. No mi. No mi. because the R double dot, the MI double dot gives you F, so there's no MI. I cross Fi is called the torque. Every force acting on a particle exerts a torque on it. The magnitude of torque is Ri cross Fi. So this theorem says that the rate of change of total angular momentum is equal to the sum of all torques, external torques acting on the body. All internal forces have cancelled each other, do not appear in this formula. That's why this formula is important. So, when we talk about dynamics, dynamics of course includes statics. That means no motion. So we are next going to go into two discussions. One is what happens when the body is at rest and not moving. That means that the left side has to be zero. So all the torques added together has to be zero. And that's the science of statics. But there's also the science of dynamics, and we have to examine this equation more in detail. We'll do that the next time.